Hey, look at all you bright, shining students.
Good morning.
Morning. All right. Okay. Questions? Yeah, Anna.
So for the book homework last night, I wasn't quite sure how they were telling, like I felt like I could draw them, but then in the solutions it would break it down by like XY plane, XZ plane instead of the eigenvalue planes. How can you tell like where it's going with like just a simple drawing?
Yeah, good question. Let me take a look. Give me an example. Which one are you?
Well, like number 5, that just the first one, they say that like in the I think in the Z plane, it's a saddle, and in the XY plane, it's a source. Let me look. Make sure I'm getting that right. Yeah, a sink on the Z phase line and a saddle in the XY phase plane. And I was just kind of confused about that wording. I don't know if you'll be able to see, but this is the
Oh yeah, look at that. Nice pictures. Yeah. Wait, this is number 5?
Yeah.
I'm not seeing that kind of language in number 5.
Like it's in the solutions. They don't ask for it in the question. Or it's like,
yeah, so the point with number 5 is that so they say the system partially decouples, which means let's go over number 5. This is the one with the matrix 2, 3, 0, 3 minus 2, 0, 0, 0 minus 1.
Yeah.
All right, so let's see. Let me share my screen. No. Y'all see that? Okay, so we've got so for number 5, we've got 2, 3, 0. Oh, sorry, minus 2, 3. All right, so there's the system. So just to remind you all, they say this partially decouples. So what that means, if we remember, this is shorthand for a system. You have to multiply this by x, y, z to get dx, dt, dy, dt, dz, dt. So this, if you were to actually multiply the matrix times the vector, you'd get minus 2x plus 3y plus 0z. You get 3x minus 2y plus 0z and 0x plus 0y minus z. And all of that, this equals dx dt. This is dy dt. And this is dz dt. Right, now we can rewrite that again. That first equation is minus 2x plus 3y equals dx dt. The second equation is 3x minus 2y equals dy dt. And the last equation is minus z equals dz dt. Does everybody see that? So what they mean by it partially decouples is that this is just happening in the xy plane. So you could just do this as a two-dimensional problem where it's just acting on the xy plane, and this is just happening on the z-axis. And they say it acts in one way on one plane and in a different way on one axis, so now draw the plane and draw the axis. So that, I mean, I'm just going by the instruction. I don't know what the answer looks like that they give you, but that's how I'm reading these instructions. The instruction says, sketch the two-dimensional phase plane and the one-dimensional phase line for the decoupled system. So we've got the two-dimensional phase plane in this sense is the XY plane, and the one-dimensional phase line for this system is the z-axis. And here's the z-axis. This is acting on the XY plane. So I would think, I don't, again, like, I don't know what answer they gave you, but I would think they want something where, let's see, -2, 3, 3, -2. What did the eigenvalues of that turn out to be? Did you do that one, Anna? Your mic's off.
The eigenvalues for the whole system are 1, -1, and -5.
And -5
That's for the 3 by 3.
for the original 3 by 3. I'm going to guess 1 and -5 were just this part of it, though. Right, because the -1 looks like it's coming from this part of it. Well, we can do it. Let's just do it real quick. -2 minus lambda 3, 3 minus lambda, and -2 minus lambda. Determinant gives us -2 minus lambda squared minus, oops, 9 equals 0. That's 4 plus 2 lambda plus lambda squared minus 9 equals 0. That's lambda squared plus 2 lambda minus 5 equals 0. And that factors 2 lambda minus 5 and lambda. Oh. No, it doesn't factor. Does that factor? Did I do something wrong? Oh, I did do something wrong. This should have been a 4. So that's a 4. That's better. So that's lambda minus plus 5, lambda minus 1 equals 0. So lambda is 1 and minus 5. Good. All right. So this 2 by 2 system has eigenvalue 1 and minus 5. So in the xy plane, it just looks like a saddle. So I haven't figured out the eigenvectors yet, but we get some sort of saddle thing just in the xy plane. And then along the z-axis, well, again, the system partially decoupled. So in the z direction, we have this thing. Excuse me. So that looks like a sink along the z-axis. So I feel like the answer they want is this picture in the xy plane together with this picture on the z-axis. Does that answer your question? Is that not what they drew?
No, that looks right. Okay, I just didn't understand the decoupling part of it.
Yeah, great.
Thank you.
Sure. Anybody else have homework questions?
It's just a follow-up question for that problem. So
Yeah.
we're always going to have to draw two graphs, or is it only when it's decoupled?
Yeah, this is a pretty specific problem where things are decoupling. Generally, the system doesn't decouple, so there's no way to kind of separate what's going on into different directions. Generally, we have the pictures normally look much more like what we saw in class last time. Things like we've got X, Y, and Z, and then there's some axis where maybe things are moving away from the origin, and maybe there's two other axes where things are maybe spiraling around the origin or something. And so off of that, things are spiraling around and moving away from the origin, that sort of thing. So I wouldn't say that's a decoupled system. I mean, I suppose one thing I could ask you, I could say, maybe I could give you a problem where I just gave part of it away. I could say, on some plane in space, this looks like a spiral source. Just draw that plane, right? So then I'm just asking you to draw this plane right here. But even that would be kind of unfair because how do you're going to get some eigenvectors and they're going to be three-dimensional eigenvectors. So how would you draw that? Something I don't. Yeah, I'm not even sure how I would phrase that question. Any other questions? Good. Are there more questions, or should we move on? We're going to jump into chapter 5. All right, let's do it. Oops. All right, chapter 5. So we're skipping chapter 4 for now. Again, we probably will come back to chapter 4. There's a lot of interesting applications in chapter 4, so we'll come to that. But chapter 4, we're dealing with non-autonomous systems and non-homogeneous systems. So the math is a little bit different. Chapter 5, somehow we're back to autonomous systems. So I don't know why the book bounces around so much. So since we've been working on analyzing systems without a function of t on the right-hand side of the system, we just finished a complete analysis of linear systems where there's no functions of t. So the next thing to do is to bump that up to nonlinear systems and figure out what's going on. So let me remind you how this worked. We did this in one dimension, and I'll remind you how this worked in one dimension, and then we'll jump up to 2 dimensions, and then again, if you want to do this in 3 dimensions, 4 dimensions, it's not much different. So just as a reminder, the book doesn't do this, and I don't know why, because they laid all the groundwork for it before. But let's say I have a system like dx dt equals x squared minus x, right? And I asked you to draw the phase line. Right. So what's the first step? Draw the phase line. What's the first step?
Is the phase line the vertical thing with the equilibrium points? So we'd want to find the equilibrium points.
Find the equilibrium points. Yep. Same thing. Find the equilibrium points. So you say dx dt equals x squared minus x, and you just set that equal to 0. Right? This is x times x minus 1 equals 0. So x equals 0 or 1. Right? So now we have this phase line we're trying to construct, and we know we have an equilibrium point at 0, and we have an equilibrium point at 1. Okay? And then things point either up or down in each. So the phase line is now divided into 3 segments by those equilibrium points, and then you have an arrow that goes up or down in each of those 3 segments. So how do we tell if the arrow goes up or down?
Plug in different values.
Yeah, that's one way to do it. We could just take a value like 1/2, plug it in, and see if we get positive or negative. We saw actually a couple ways to do this. Let's just talk about a slightly more sophisticated way that we did talk about. If we just want to understand what the system looks like right here around this equilibrium point at 1, one of the things we did was we said, hey, this is a function of x. Let's graph that function of x, right? So we have the system dx dt equals x squared minus x. And now let's look at x squared minus x as a function of x. Okay, what does that look like? We know it has roots at 0 and 1. And what shape is it?
It's a parabola that goes up, that opens up.
Upward pointing parabola. Good. Okay. All right. Now, if I want to understand this system around 1, that's the same as trying to understand this picture right around that point. Yeah? Okay. All right. So let's take a step back just for a second. Let's look at a simpler system just for a minute. Let's look at the system dx dt equals 3x. All right, first of all, well, we can do the same sort of thing. We know everything about this. We've got a single equilibrium point at 0. 3 is positive, so things move away from the origin. We can graph x versus 3x, and we get just a line of slope 3. And so we've got the phase line. And the other thing is we know what solutions look like. We can graph x versus t because we know explicitly what the solutions look like here. What is the solution to this? If I want x as a function of t, what does that look like? Trying to jog your memory here from earlier in the semester. We're just doing one-dimensional systems. How would you solve that system? The very first one on the very first day. Give me a function whose derivative is 3 times itself.
You can integrate.
You can also, it's a separable system. You can separate, yeah. Or you could,
It's like e to the 3 something.
yeah, e to the 3t.
Yeah.
Right, times any constant. Right, e to the 3t times any constant. If you differentiate that, you get 3 times e to the 3t times the same constant. Okay, so it's definitely a solution. We can graph those for different values of c. We get either an exponential graph that goes up if c is positive, or if c is negative, we get an exponential graph that goes down. Okay. So these are the solutions for various values of c. Okay, and the slope of this line tells us how fast these solutions are increasing or decreasing. Right, the slope of this line is 3, and this solution is something like e to the 3t. So the slope here tells us how fast we're moving away from the origin there. All right. This is just a review. I'm reviewing. I hope I'm jogging your memories. Give me a thumbs up, thumbs down, something. Does it look familiar? Okay, good. I'm seeing Amber looks totally bored, which is good. When I'm reviewing like this, I'm hoping people will be bored. All right, now let's go back up. I'm trying to understand this system up here, but I just want to understand it around this point. So let's just kind of blow up that point there. This looks like, if I just magnify that point, it looks like I've got the x-axis, I've got this point, and I've got this curve going through it. And if I blow that up real big, that curve just looks like a line. What line does that curve look like? How do I figure out what line that is?
Isn't that the derivative?
Yeah, this line right here, well, the slope of that line is going to be given by the derivative. Okay, what's the derivative of x squared minus x at that point? That's the point where x equals 1. The derivative is 2x minus 1. If I evaluate 2x minus 1 at the place where x equals 1, what do I get?
1.
1, right? 2 minus 1 is just 1. So the slope equals 1. Good. All right. Which means this looks like the line y equals x. If you just zoom in on this blue area, this blue point, then what we see is a line that looks like the line y equals x. Okay. That's called linearization. When you focus in on a critical point and you say, what linear system does that now look like? Looks like the linear system y equals x, which means solutions will move away from that point as if they were solutions to the differential equation dx dt equals x. Okay, solutions near that point behave just like solutions to this system, and this is the system dx dt equals x. So we've linearized the system by replacing it with a linear system whose slope is the derivative of the original system, because the derivative tells you what line it looks like. Okay, and that's what we can use that. I mean, we know what this system looks like. This system that has a very simple phase portrait, things just move away from the origin, right? And that tells us back in the original phase portrait that around 1, things have to move away from 1. Right? Because this picture of the linearized system looks like this picture locally of the nonlinear system. Right, so I'm just going to keep like saying this in lots of different ways until it starts sinking in for everybody. The original nonlinear system, x squared minus x, near the point where x equals 1, looks a lot like this linear system down here near the point where x equals 0. Right, now x equals this linear system down here where x equals 0 just looks like a source, which means this nonlinear system near where x equals 1 looks like a source. So we can tell if we have a source or a sink just by looking at the associated linear system right around that point. Y'all buy that? All right. If that's making sense to you, if that doesn't make sense to you, please stop. And I could say it in like 10 other different ways. But I'm sensing boredom, so I want to go on. We want to
Great,
do the
Professor.
same thing now for two-dimensional systems. Yeah, Sarish.
So basically, like you have this nonlinear system, and then you're just taking the derivative to find like how it behaves at one of the equilibrium points.
Yeah,
Or so are you basically allowed to linearize at any point?
just at
Or
the
does it have
critical
to
points.
be
Just
at
at
the
the, yeah. Because we're only analyzing, I mean, yes, you could, absolutely, you could linearize at any point to find the local behavior at that point,
Mhm.
but it's only going to lead us to drawing nice pictures if we do that at the critical points.
I see.
At the equilibrium points, sorry, not the critical points, the equilibrium points, yeah. Here, let's just look at another system. Let's just do this one more time. Let's say I had a system, I'm just gonna now just make up some complicated looking crap. Dx dt equals x cubed plus 3x minus sine of x plus square root of x minus 1. Okay, I just made up something complicated, okay? And let's pretend that the graph of this thing looks like, goes up and down and down and up and down, whatever. Okay. All right, that means the way I've drawn it, there's 3 equilibrium points for the phase line. So if I'm trying to draw the phase line, I'm going to see 3 points here. And the behavior around this point will look like the behavior around this point. The behavior around here, the middle one, will look like the behavior around here. And the behavior around the top one will look like the behavior around here. Okay, now this red point looks like, if I were to kind of blow that up to a red circle and just focus in real close, that's going to look like some linear system, right? And whatever linear system that is, that's going to have a phase line. And that phase line will be a source. And that little local picture is exactly the picture that I see up here. Right, I'll see this little local picture of a source. And then the same thing over here. If I blow up the blue circle, then again, I see this other system, which maybe looks like a line of different slope. Okay, it has some phase line. It's also a source, but maybe things are moving away from here at a different rate. Whatever rate they're moving away from, that's what I'm seeing up here. Is that making sense? I'm trying to build this phase portrait by piecing together smaller phase portraits. And those smaller phase portraits are just the phase portraits of these linear systems. That's exactly, I'm trying to do this real slow to convince you when we go into 2 dimensions that what we're doing is the exact same thing. So in 2 dimensions, if I have a 2-dimensional nonlinear system, I can at least get the phase portrait of that system near each equilibrium point by linearizing around each equilibrium point and just drawing the picture of the linear system near each equilibrium point. Right? That's the philosophy here. We have this complicated nonlinear picture, and the way we're going to get that is by drawing smaller pictures of the linear systems around those pictures. All right, so let's do it. Okay, but first I want to make sure everybody caught one of the earlier things we said. The way you get this function is by evaluating the derivative. That gives you the slope, okay? Then the function itself, right? So here the derivative, if the derivative is 3, then the function is 3x. And if the derivative equals 3, then the function is y equals 3x. Or dx dt equals 3x is the system. All right, so we're jumping up in dimension. So now we have t is our dependent variable. Sorry, t is our independent variable. X and y are our dependent variables. So now instead of taking the derivative with respect to x, since we have multiple variables flying around, we have to take the partial derivative with respect to x. Right? So if I have some system, some complicated system, dx dt equals, and I've got some function of x and y here, and then dy dt, and I have some other function of x and y here, okay? And I have an equilibrium point at x0 comma y0, then the linear system near x0, y0 is going to be the following. It's the partial of f with respect to x times x plus the partial of f with respect to y times y. The partial of f with respect to x, sorry, g with respect to x. Partial g with respect to y, y. This is dx dt. This is dy dt. Okay, And these partials are just numbers because I'm actually evaluating them at that point x0, y0. So you find the partial, then evaluate the partial at that equilibrium point, and that becomes the coefficient of x, and the other partial is the coefficient of y. Right? Some of you who were bored are probably now totally confused. So we'll work out some examples. Okay. So the first example here is the easiest example is going to be the logistic equation.
Master students don't go through.
You know, I've got to sign off just for 1 second here. Okay, let me pause here.